in sci-fi, whether it's like Marvel's Kitty Pryde phasing through walls or the Enterprise finding a way through shields in Star Trek, defying reality is always the coolest power. That idea of fusing through something solid, that's quantum tunneling. But what if I told you it's not just for, tiny atoms? What if a whole electrical circuit big enough to hold could do it?
Well, that leap from sort of sci-fi concept to actual tech, that's exactly what we're diving into today. We're looking at the research that landed John Clarke from UC Berkeley, Michel Devoret from Yale and UC Santa Barbara, and John Martinis, also from UC Santa Barbara, the 2025 Nobel Prize in Physics.
Wow.
Yeah, they proved something called macroscopic quantum mechanical tunneling, MQT, and also energy quantization, but in circuits we build.
Okay, so our mission here is to really get our heads around how huge this was.
Yeah.
They didn't just see quantum weirdness. They, built a device, right? Metal, ceramic, behaving like one giant quantum particle.
Exactly. This is really where the microscopic quantum world met the macroscopic things we can actually engineer and use.
Yes.
And to really feel how revolutionary this was back in the 80s, we kind of need to look back a bit further. The story really kicks off in 1962.
Okay. With Brian Josephson. He predicted this really bizarre thing, that Cooper pairs, those are the charge carriers in superconductors, could tunnel coherently through a barrier. Coherently. What does that mean in this context?
Yes.
Not just random tunneling.
Right, not just one electron popping through now and then. It meant the tunneling process itself had a quantum phase, like a wave, and it was coordinated across the whole system. It creates this phase-dependent supercurrent. It was a big conceptual leap.
And someone actually built this, almost immediately. In 1963, Anderson and Rahl at Bell Labs verified it experimentally. And that experiment basically gave us the core component for all of this.
Yeah.
The Josephson junction. The Josephson junction. That's the key device, isn't it? So let's break that down. What is it in simple terms?
Well, people often call it a superconducting sandwich. You've got two pieces of superconductor, and you separate them with this really, really thin layer of something that doesn't conduct electricity, an insulator.
Like the filling in the sandwich doesn't conduct.
Exactly.
But here's the quantum magic. That tiny non-conductive gap, it actually allows those Cooper pairs to tunnel across anyway, and they carry a supercurrent, meaning zero voltage drop.
And critically, this makes the junction a non-linear inductor. That's what separates it from, your standard classical circuit components.
Gotcha. So Josephson predicted it, Bell Labs built it, but there's still more theory needed.
Yeah, there was another piece. Caldera and Leggett in 1981, they provided the theoretical framework for understanding how quantum behavior could actually survive in what we call dissipative systems.
Dissipative, meaning systems that lose energy. Like real-world systems, not perfect theoretical ones.
Precisely. Real circuits have resistance, they interact with their environment, they lose energy. Caldera and Leggett figured out the math for how quantum effects, like tunneling, could still happen despite that dissipation. That was vital for making this practical.
Okay, so the theory was solidifying, but building it, making something macroscopic act quantum.
That sounds hard.
Oh, incredibly hard. Which brings us to the actual Nobel-winning experiments in 84 and 85.
Yeah.
Clarke, Devoret, and Martinis at UC Berkeley.
Yeah.
The engineering challenge was, frankly, monumental.
What made it so tough? What were they fighting against? Noise. Just ambient energy. Think about it. Quantum effects are incredibly delicate. To see them in a macroscopic circuit, you have to shield it from everything. Thermal energy, stray electromagnetic fields, vibrations. Any tiny disturbance could just wash out the quantum signal and make it look classical. It sounds like they needed to put their circuit in, like the world's quietest room, a sensory deprivation chamber for electronics.
That's a perfect analogy. They went to extraordinary lengths. They designed these incredibly complex filter chains, think over 200 decibels of damping across a huge frequency range.
Well, they used newly developed copper powder microwave filters, and they anchored everything meticulously at different temperature stages in their cryostat, their super refrigerator, specifically to block thermal black body radiation from getting in.
So it wasn't just about making it cold, it was about making it silent electronically.
Exactly. They had to eliminate every possible classical explanation for what they might see. That incredible attention to detail, the engineering required to isolate the system so perfectly, that itself was a wow moment. It let them actually measure all the parameters and compare them quantitatively to the theory. Okay, so they've built this ultra-isolated, super quiet circuit. Stage is set. What do they actually see? Let's start with the first big one. Macroscopic quantum tunneling, MQT.
Right. So MQT showed up when the system escaped from a state where it had 0 voltage across it. Imagine the system state as a marble sitting at the bottom of a bowl.
Okay, trapped.
Trapped. Classically, to get out of the bowl, the marble needs enough energy to be pushed over the rim.
But their circuit, the superconducting sandwich, it didn't climb out. It didn't climb. It just appeared outside the bowl. They detected voltage suddenly appearing across the junction, even though based on classical physics and the energy they knew it had, it should have stayed tracked at 0 voltage.
It tunneled, phased right through the barrier like Kitty Pryde. It tunneled through the potential barrier. And here's the really mind-bending part, the core insight. The entire system, all those Cooper pairs moving together throughout the circuit, behaved as if it were one single, unified quantum object.
Wait, so you're saying it's not just like one little particle tunneling. The whole thing, this macroscopic circuit we built, acts like one quantum particle.
That's the macroscopic part. It's not just electrons, it's the collective behavior of the entire superconducting state in that circuit.
That's wild. It's like the whole wall becomes a ghost, along with Kitty Pryde.
It's a good analogy for the scale difference.
Yeah.
And the variable that actually describes this collective quantum state, it's the phase difference across the junction, usually written as theta.
Okay, why is that phase variable, theta, so important? What's the big deal about that? Because theta governs the collective quantum behavior. Classically, phase is just about how waves line up. But here, they showed that theta was acting like the position coordinate of a quantum particle.
Like where the particle is in its energy landscape.
Exactly. And by changing the physical properties of the junction, the thickness of that insulating barrier, the size of the superconductors, they could actually engineer the potential energy landscape for this theta particle. They could control its quantum behavior.
So they weren't just observing a quantum particle, they were effectively building one, designing its properties.
Precisely.
Which leads directly to the second huge finding, energy quantization.
The quantum staircase.
Right. Classical systems can have any amount of energy, like walking up a ramp. Quantum systems can only have specific, discrete amounts, like steps on a staircase.
You can only be on step 1 or step 2, nothing in between.
Correct. And they proved this for their macroscopic circuit. They shone microwaves on the junction. Now, if it were classical, it would absorb energy kind of smoothly across different frequencies.
But it didn't. It only absorbed microwaves at very specific frequencies. And those frequencies corresponded exactly to the energy needed to jump from one quantum energy level one step to the next higher one.
Okay, this feels like where it gets really practical. Making a circuit that only accepts specific energy packets?
Yeah.
What does that do for us?
It makes the circuit a near-perfect, controllable two-level system. You have the ground state, the lowest step, and the first excited state, the next step up. That's your fundamental 0 and 1.
The qubit.
The qubit. They had experimentally demonstrated that this macroscopic circuit could function as an artificial atom, a quantum system with properties they could engineer. This really opened the door wide for circuit quantum electrodynamics, or CQED.
And that artificial atom idea, that's the direct ancestor of the qubits that companies like IBM and Google are building today, isn't it? Like the transmon qubit.
Absolutely. The transmon, which came out around 2007, is a direct descendant. It's specifically designed based on these principles to be less sensitive to noise while keeping those nice, distinct quantized energy levels.
And the progress since those first experiments.
It's staggering. We've gone from, demonstrating the basic physics in one junction to processors with over 1,000 qubits. And maybe even more importantly, the coherence times, how long the qubit can maintain its quantum state, have improved by something like 6 orders of magnitude.
Wow. 1,000,000 times better. That's incredible.
It's what makes actual quantum computations start to look feasible.
Okay, so computing is one massive application. What are the other big one you mentioned? Quantum sensors. Tell us about squibits.
Right, SQUDs, superconducting quantum interference devices. These things are basically the ultimate magnetic field detectors, leveraging the quantum coherence of the Josephson junctions.
How sensitive are we talking?
We're talking sensitivity approaching the fundamental quantum limit. They can detect changes in magnetic flux down to a few microflux quanta. It's an absurdly small amount of magnetic field change.
Okay, that's ridiculously sensitive. Where do you even use something like that?
Well, in medicine, they're crucial for magnetoencephalography, MEG scans, which map the tiny magnetic fields produced by brain activity. Much more sensitive than EEG.
Ah, so peering into the brain non-invasively. Come on.
Yeah. Also used in geology for finding mineral deposits deep underground by detecting subtle magnetic anomalies. And in fundamental science and metrology, Josephson junctions are used to define the standard volt with quantum accuracy.
So brain scans, finding buried treasure, defining our electrical standards.
Yeah.
And I think you mentioned security, too.
That's right. The same underlying quantum principles enable things like quantum key distribution, QKD, for cryptography, creating encryption keys that are theoretically unbreakable because of quantum mechanics. The tunneling circuits of the 80s are now helping guard secrets today.
It really shows how this, like, super abstract physics from decades ago creates real-world high-value applications now. Billions of dollars worth, right? Quantum sensing is projected to be huge.
Absolutely. The market is growing fast, projected near $1 billion by 2030. And the research isn't stopping. People are building directly on Clarke, Devoret, and Martinis' work to make even better qubits.
Like what? What's next for qubits?
Well, there are designs like fluxonium qubits, engineered for even better protection against certain types of noise, and things called cat qubits, which use a clever trick involving engineered noise to make them more error-resistant. The big goal now is fault tolerance, making quantum computers that can correct their own errors.
Okay, but it can't all be smooth sailing. As we try to scale up from one or a few artificial atoms to thousands, maybe millions, what are the big roadblocks?
Oh, the challenges are definitely steep. Number one is still decoherence. That's the enemy.
Losing the quantumness.
Exactly. Keeping these systems perfectly isolated from everything, heat, vibrations, stray fields, gets harder and harder as systems get bigger and run for longer. Any interaction with the outside world can make the quantum state just collapse.
That sensory deprivation chamber needs to be absolutely perfect and huge.
Pretty much. Then there's scalability. Making thousands or millions of qubits that all work perfectly and identically is tough. You also get problems like crosstalk, where operating one qubit accidentally affects its neighbors.
Like electrical eavesdropping between qubits.
Sort of, yeah. And finally, fabrication. Making these Josephson junctions consistently, with nanometer precision, reliably, millions of times. That requires incredibly advanced manufacturing techniques that are still being refined.
So fundamental physics proved, path to technology clear, but major engineering hurdles still ahead. Got it. This deep dive has been fascinating, from a theoretical quirk to the bedrock of quantum tech. Let's try to boil it down. What are the three absolute key takeaways for everyone listening?
The 2025 Nobel Prize essentially proved quantum mechanics isn't just for the ultra-small. They showed a macroscopic, human-made electrical circuit that Josephson junction could behave as a single quantum entity, demonstrating MQT.
That discovery wasn't just an observation. It was enabling. It turned that junction into a programmable, artificial atom, giving us the physical basis for the qubit, which is the heart of quantum computing.
These quantum principles aren't just futuristic, they already power critical technologies today. Ultra-sensitive SWIDA-wides for brain scanning and resource discovery, quantum voltage standards, and even the beginnings of quantum-secure communication. Amazing. Clarke, Devoret, and Martinis really did lay the foundation for whole new industries, didn't they? It feels almost like the invention of the transistor, something fundamental that just changes the landscape. They taught matter how to be quantum on our scale. So the big question I want to leave you with is this. If we learned to engineer quantum tunneling and energy levels into macroscopic devices back then, what other fundamental physics, maybe something we think is confined to particle accelerators or black holes today, might we eventually engineer into the devices of tomorrow?